30 years after its inception, the James Webb Space Telescope, JWST, was finally launched from French Guiana on Christmas Day 2 years ago. On December 28, it passed the Moon, and by January 24, it fired its engines for 5 minutes before entering its final orbit, 1.5 million kilometers away from Earth. After weeks of meticulous deployment, it captured its first image on July 12 of last year, revealing distant galaxies as they appeared over 13 billion years ago. Since then, the Webb telescope has continued to expand upon this groundbreaking achievement, seemingly lifting the boundaries of human exploration, ushering in a new era of astronomy and space research. These recent images are testament to both humanity's capacity for discovery and the vastness of the universe, highlighting our role in its ever-expanding scope. Join us as we delve into the latest images captured by the JWST, revealing the secrets of the cosmos. Although telescopes don't literally peer into the past, when they observe light from distant galaxies, they are witnessing light that has traveled across the cosmos for billions of years. Technically, telescopes capture the current state of that light, which has remained mostly undisturbed as it traveled through the vacuum of space. The light pattern we observe today is the same as when it was first emitted by those distant galaxies. This means we can infer the universe's appearance from billions of years ago by studying light in its present form. It's similar to looking at a photograph of your child from years ago. The photo represents a moment from the past, though your child has since grown and changed. You aren't literally seeing into the past, but rather observing a pattern from a past moment. In much the same way, we can deduce the distant universe's past by analyzing the light that reaches us today. Although the light has traveled vast distances, it hasn't changed in any way we can't account for. One notable alteration is redshift, caused by the universe's expansion, but scientists are adept at correcting for this, allowing for a clearer picture of distant galaxies as they were when that light first left them. Before the JWST, only a few galaxies were known to exist from the universe's early stages. The telescope has now uncovered hundreds of ancient galaxies, some of which could be among the universe's first inhabitants. According to a recent study, these youthful galaxies exhibited intricate structures and star-forming clusters as early as 600 million years after the Big Bang. This study is part of the JWST Advanced Deep Extragalactic Survey, which gathered data over a month from 2 sections of the sky, one near the Fornax cluster and another in the constellation Ursa Minor. In this time frame of the universe, if the entire universe's history were compressed into a 2-hour film, we're witnessing the first 5 minutes. Kevin Haynes, a research professor at the Steward Observatory in Arizona and lead author of the study, describes these galaxies as the early builders of the complexity seen in the modern universe. These findings shed light on the origins of galaxies and stars, which paved the way for the diverse elements and structures we see today. The study revealed 717 young galaxies in this early phase, which shows that the universe was between 370 million and 650 million years old. These galaxies, spanning thousands of light-years, display intricate structures and are actively forming stars in various clusters. Prior to this discovery, the earliest galaxies visible appeared only as small smudges. These smudges, however, represented millions or even billions of stars forming at the dawn of the universe. Thanks to JWST, we can now see them as extended objects with discernible structures. Many major space telescopes, including Hubble, the Chandra X-ray Observatory, and NASA's retired Spitzer telescope, conducted significant research on these 2 regions, collectively referred to as Good South. Yet, 93% of the galaxies uncovered by JWST during the survey had never been observed before. Prior to this, only the brightest, most extreme cases of early galaxies were visible. Now, as we look deeper into a younger, more chaotic universe, we're seeing more ordinary galaxies. Galaxies that represent the typical conditions of the early cosmos. There has long been debate about how the universe transitioned from this turbulent, dusty state to the transparent universe we observe today. One popular theory suggests that this transformation, known as the epoch of reionization, occurred about 400,000 years after the Big Bang. It is thought that the first generation of stars, estimated to be 30 to 300 times more massive and thousands of times brighter than our Sun, formed and illuminated the previously dark universe, breaking apart hydrogen atoms into protons and electrons. This ultraviolet starlight is believed to have reionized the universe, a process that continued for a billion years after the Big Bang. However, some researchers argue that supermassive black holes, like the one at the center of our Milky Way, may have played a significant role in this process. They suggest that outflows from these black holes allowed ultraviolet radiation to escape galaxies and could have influenced cosmic evolution more than previously thought. A second research team, investigating galaxies that formed between 500 and 850 million years after the Big Bang, equivalent to between 5 and 8 minutes of our 2-hour film analogy, believes they may have found the key to understanding how star formation influenced the early universe's evolution. In this later stage of cosmic history, the team is observing the impact of galaxy formation on the structure of the larger universe. Galaxies in the early universe were far more chaotic in their star formation processes, and the team is working to comprehend how this star formation ionized the gas within those early galaxies, shaping the universe's eventual transparency. These groundbreaking observations by the James Webb Space Telescope continue to reveal the mysteries of the universe, taking us back to its formative moments and offering new insights by into its evolution. Particles emit radiation as they cool and converge with other particles. Specialists have discovered that 1 in every 6 early galaxies displayed strong emission lines in their spectrum. These lines indicate that early galaxies were actively producing stars, resulting in bursts of ultraviolet photons. In turn, these early stars were critical in driving cosmic reionization. The findings suggest that these strong emission lines are common in the early universe, pointing to vigorous star formation. The research team found that nearly every galaxy observed from this era exhibited these intense emission lines, indicating they were efficient at creating hot, massive stars. Based on these emission lines, they inferred that galaxies in the early universe formed stars in short, intense bursts, followed by dormant periods. A deep processed image from the James Webb Space Telescope, JWST, released in July 2022, revealed hundreds of galaxies as they appeared in the early universe. Many observers were struck by how oddly distorted some galaxies appeared, almost as if they were melting or twisted, a visual distortion due to gravitational lensing, rather than their actual form in space. The presence of multiple galaxies in the same image, such as in the case of the massive galaxy cluster RxJ20229, adds to the illusion of identical twins. This duplication occurs due to gravitational lensing, a phenomenon predicted by Albert Einstein's theory of general relativity over a century ago. Gravitational lensing occurs when a massive object, like a galaxy cluster, bends the light from more distant objects behind it, magnifying and distorting their appearance. The effect of gravitational lensing can result in repeated warped images of the same object, sometimes forming interesting shapes, like crosses or the famous Einstein rings. These fascinating patterns provide cosmologists with valuable insights. Lensed objects not only amplify light from distant sources, but they also offer clues about the mass distribution of the intervening galaxies and galaxy clusters. One of the significant discoveries made using JWST is the detection of water vapor in the atmosphere of a gas giant exoplanet, WASP-18b, which orbits its star in less than 1 Earth day. WASP-18b is more than 10 times the mass of Jupiter, and its atmosphere reaches extreme temperatures of about 5,000 degrees Fahrenheit 2,760 degrees Celsius. Despite the heat, JWST's observations revealed faint signatures of water vapor, a testament to the telescope's sensitivity. Previous observations by telescopes like Hubble, Chandra, and Spitzer could not detect the subtle water features in WASP-18b's atmosphere. The detection of these water signatures by JWST was an unexpected discovery, shedding new light on the complexities of exoplanet atmospheres. WASP-18b is a massive, tidally locked planet, meaning one side always faces its parent star, causing it to be intensely hot. The presence of water vapor on such a planet is a testament to JWST's extraordinary capabilities. The data gathered not only provide clues about the planet's atmospheric composition, but also open up new avenues for studying other exoplanets. JWST represents a monumental leap in our understanding of the universe. Beyond stunning imagery, the telescope provides essential data that help scientists unravel the formation and evolution of galaxies and star systems over cosmic time. By analyzing light from distant objects, researchers gain insights into their composition, age, and the processes that led to their formation. One of the most exciting aspects of JWST is its ability to probe the atmospheres of exoplanets, detecting molecules that may be crucial for life. This capability could revolutionize our search for habitable planets beyond our solar system. JWST's infrared technology allows it to peer through cosmic dust and gas, often obstructing observations at other wavelengths. Additionally, the telescope is poised to answer key questions about dark matter and dark energy, two mysterious components that constitute a significant portion of the universe. By mapping the distribution of galaxies and clusters, researchers can infer the gravitational forces at play. This ongoing research will refine scientists' models of cosmic evolution and the overall structure of the universe, offering deeper insights into the nature of dark matter, dark energy, and the fundamental forces that shape the cosmos.